Okay, good morning. So today we're going to have a slightly abbreviated lecture because we're having a quiz, the second quiz. So today I want to continue with our discussion of screw motions and how to describe the forward kinematics using screw motions, which leads to something that we're going to call the product of exponentials formula. Okay, so let's review the main result from screw theory. Okay, and everything goes back to a result by Schall and Motzi. So we decided to be fair and call it Schall-Motzi theorem. Okay, and basically this theorem says that every rigid body motion can be expressed as a screw motion. Okay, so let's illustrate that in pictures. So we have some screw axis. Let's draw two frames. Here's frame 1. And here is frame 2. Okay? All right, and let's draw the fixed frame. Say here. Okay, so there's the fixed frame. Okay, so if I want to move frame 1 to frame 2, then this can be done by a screw motion. So what is a screw motion? Well, there's a screw axis. You rotate around that axis, okay, by some angle theta. And at the same time, you translate in the direction of the axis by some distance d. Okay, so something like that. So let's call this distance d. Okay. All right. So use a screw axis over here. Okay, so Schall and Motzi said that every rigid body motion can be expressed in this fashion, as a screw motion about some screw by some angle theta and by some pitch. Okay, pitch times the angle. So h is the pitch. We're going to define that to be d over theta. Okay, so this is the screw pitch. Okay, so we came up with a formula. Okay, so given T01 to be of this form and T02 of this form, let's call it R prime P prime 01. Okay, then we said that T02 is the following. Okay, 0, I minus e to the q plus h hat. Okay, there's a 1 here, and multiplied by T01. Okay. Okay, so let's explain what these things mean here. So Q is some arbitrary point on the screw axis. Okay, and so this vector is Q. Okay, and we get this formula by observing that the origin of frame 2, that's P prime, okay, P prime can be expressed as the sum of this vector plus this vector plus that vector. Okay, it's the sum of these three things. So now let's start with the easy one. What's this? Well, this vector is just h times theta. Okay, so h times theta is the distance d in the direction omega hat. Okay, so what's omega hat? Omega hat is just the a unit vector in the direction of the screw axis. Okay. And now this part, so what's this? Well, this is just a rotated version of that vector. So this vector is p minus q. Okay, so if we rotate p minus q around this axis, that can be expressed as e to the omega hat theta times p minus q. Okay. All right, so we use this picture to come up with this formula. Okay. And the key result from last time is that instead of writing the matrix this way, okay, it's hard to remember. Okay, we're going to write this as a matrix exponential. Okay, omega hat 0, v0 times theta times t0, 1. Okay, so this matrix here is expressed now as a single matrix exponential, where the of this matrix. Okay, and so how do we choose v here? Okay, so if we choose v to be minus omega cross q plus h omega, let's put the hats back. Okay, then everything works out. Okay, this becomes this. Okay, and I asked you to verify that in fact this is true. Okay, and it's good practice because it makes use of a lot of formulas, tricks that we used in this class. Okay, to simplify operations like the multiplication of a rotation matrix with a symmetric matrix followed by a rotation inverse, so on. Okay. All right, so with this choice of v, this is the same as that. Okay. We also have a closed form formula for evaluating this. Okay. This turns out to be, well, the rotation part is as expected, that. Over here, okay, the vector part can be represented this way. Okay. So now the question is, what's g sub theta, or g theta? Turns out g theta is I theta plus 1 minus cosine theta times omega hat plus theta minus sine theta omega hat square. Okay? All right, so we have a closed form formula for calculating the matrix exponential. Okay, and it looks similar to the formula for the exponential of a skew symmetric matrix. Okay, but there's slight differences, right? Okay, so this is going to be our good friend, okay, today and throughout the rest of the course. Okay, all right. So let's think about how can this help us write down the four kinematics. Okay, so think about this. Okay, a screw motion. Okay. We rotate around the screw axis by some angle theta, okay, and then slide along that axis at the same time. Okay, the direction of the screw axis, okay, is given by some unit vector omega hat. Okay, angle is theta. Everything is expressed with respect to the fixed frame. Okay, omega hat, q, p, everything. Okay. All right. So let's erase this picture.